Hi, this is the another video for chapter 8. So let's look at what I'm going to cover here. I'm going to try to cover these three sections from chapter 8. Last time we talked about polar form of complex numbers. Now we're going to see why we put them in polar form, because it is much easier to multiply, divide, and raise complex numbers to powers in complex form. So we're going to talk about that. Then we're going to talk about parametric equations and graphs, and then finally vectors. See if we can put them all in one video. Okay, so again, I hope you're doing well, and as you know, since we are not meeting face to face, you can watch these videos, and also I'm going to have Blackboard collaborate that during the regular class hours. I'm going to be in Blackboard, and if you have any questions, show up and ask. And also there is a Blackboard collaborate on the in Blackboard site that you can participate yourself and maybe do group study in virtually online. And that is also, I think I put it in an announcement already. All right, so let's start. So I'm gonna first, as usual, get rid of my picture that is taking part of the screen. So that's what we're going to do. So let's start. So we are going to talk about complex numbers. Now, how do we multiply two complex numbers? Now, before in algebra, you learned that to multiply complex numbers, for example, if you have 2 plus 3i, and we want to multiply it by, let's say, we want to multiply it by another complex number, let's say 3 minus 2i, then we would have to multiply basically like that, and then distribute it this way, and then combine the I terms and all that. Now that's fine if you have 2 or 3 complex numbers, but if you have many, or maybe if you want to take a complex number, let's say 2 plus 3i, and you want to raise it to, let's say, 120 power, how do you do that? You have to write it 120 times and multiply. It takes forever. So that's not the way we do it. The way we do it is we are going to do it in the form of complex numbers. So we're going to write complex numbers in polar form, which we talked about last time. So that's the polar form of a complex number. So let's say we have one complex number, z1, and this r1 times cosine theta 1 plus I sine theta 1. And you know, r1 and theta 1 are called modulus and the angle. And then this complex number is r2 modulus, and the angle is theta 2. Now, to multiply two complex numbers in polar form is really easy. All you have to do is multiply the moduli, modulus times modulus, and then add the angles, and that's it. You get a new complex number in polar form. Then you can convert it to rectangular if you want to, but that's how you do it. All right, so let me move this a little bit. Get this arrow. There we go. So here's an example. We have this complex number and this complex number. To multiply them, all we have to do is multiply the moduli and then add the angles. So that's all there is to it. So 4 times 2 is 8, and then 80 So Z1 80 and 145, that's 225, and then the same thing here, 225. So we get this. Now we don't have to convert to radian, but if you want you can convert to radian. But we know cosine 225 is the same as cosine 5 pi over 4, right? So that would be square root of 2 over 2 minus. Now, you know cosine 225 is about right here. That's 225. So the reference angle is 45. So that means the cosine of this would be the same as cosine of 45 except it's negative. And the sine would be the same except it's negative. So it would be negative square root of 2 over 2 and negative square root of 2 over 2, right? And that's it. That is the answer. So it's much easier to multiply two complex numbers. Now, how do we divide two complex numbers? That was even harder in algebra, right? Remember, if you wanted to divide two complex numbers, you would have to multiply by conjugates and go through simplifying. But in polar form, it's very easy. Just divide the moduli, right here. So it would be R1 divided by R2. If you're dividing Z1 by Z2, then it's R1 over R2, and it would be theta 1 minus theta 2. The same here. And of course, denominator can't be 0, we know that. Okay, that's it. So here's an example. So here's R1 and here's R2. We divide them, we get 1/2. And then 213 minus 33 is 180. 213 minus 33 is 180. Okay, we know cosine 180. What's cosine of 180? Well, it's -1. And what's the sine of 180? Is 0. So that would be 0 and that would be 1, and that's it. So 0 times I is just 0. So when you divide these two complex numbers, you just get -1/2. Plus 0i, but 0 doesn't change anything. Okay, the Moivre theorem and says that if you want a complex number, if you want to take a complex number, let's say a plus bi, and you want to raise it to, let's say, nth power, that would be really tedious to do in algebra because you have to write that, n times and then multiply. That takes whatever. So with this theorem, all we have to do is write it in polar form, which is r times cosine theta plus I sine theta. Remember, we call this form cis, right? Cis for cosine and then plus I sine. That's why it's called cis. Okay, so all we have to do is raise the modulus to the nth power, right? And then multiply the angle by n. That's it. So it's really easy to raise. So if you were to raise this to fifth power, you would have to write that in algebra 5 times and then multiply them. That would take forever, especially if that was 50 instead of 5. But now we can easily do it using, so we have to convert 1 plus I to polar form. So to convert it to polar form, we have to think of 1 plus I is right here somewhere, right? We didn't have to do all that, really. Let me erase it. So what you have to do is you have to think of, where am I doing? There you go. So here is 1 and I, which is right there. So that's the point, 1i. And then, So what we want is this distance, and we want the angle. That's it. Now the distance, square root of 1 squared plus 1 squared, which is square root of 2, and the angle is tangent inverse of 1 over 1. Now since we are in this quadrant, or in this quadrant, in these two quadrants, the calculator tangent inverse is good enough for us. If you're over here and over here, then calculator gives you the wrong ones. You have to add pi to it. Okay, so that's the polar form of it. So the polar form for this is given by that. So now, this to the 5th power is the same as the polar form to the 5th power. Now, the polar form to the 5th power would be r to the nth, which is 5th. So our r is that. So we have to write this number as square root of 2 times cosine pi over 4 plus I sine pi over 4. That's the complex number. Now if we take this and we want to raise it to the 5th power, then we're going to have to raise square root of 2 to the 5th power, right? And then multiply the angle pi over 4 by 5. And then simplify. We end up with, again, these are stuff from previous chapters. You should know how to find those. And he simplifies into -4 minus 4i. That's much easier and faster than writing that 5 times. Alright, what about the root of a complex number? Now that was something we didn't even do in algebra. We didn't talk about root of complex numbers, but now we can do that. So in algebra, when we talk about the square root of 4, for example, that is just 2. But with complex numbers, we're going to assume what? We're going to assume all the roots. So we're going to think of 4 as actually 4 plus 0 times I, which is actually a complex number. And then we're going to use this theorem. Again, roots of complex numbers, we use this theorem. So the way you take the root of a complex number, now first of all, nth root of something is the same as what? Is the same as that thing to the power of 1 over n, right? So let's see what we get here. So what we get here is, first we take so if you write the complex number as z is r and then cosine theta plus I sine theta. So if you want to take z and raise it to 1/nth power, you just raise this to 1/nth power, and then you divide theta also by n, right? But first of all, notice that it's not cosine theta divided by n, it's cosine of theta over n. So we divide theta by n and we add to it 2k pi over n, both of them. So theta over n and then plus 2k pi over n, the same thing here. And here k is going to go from 0, is an integer, from 0 all the way to whatever n is minus 1. For example, if you want to do cube root of a complex number, then you're going to pick 0, 1, and 2. And for every one of these, you find a root. That means cube root of a number is actually 3 numbers. In algebra, we said cube root of, in algebra, remember, cube root of 8 is what? Is 2. But with complex numbers, if we assume 8 is a complex number, we're going to have to find 3 roots, these 3. So let's start by looking at an example. Here's an example. evaluate the cube root of z. Now r is 8 and theta is 2 pi over 3. So we're going to write it like this. So it would be 8 to 1/3 power times cosine of 2 pi over 3 divided by n, which is 3 here, right? And then again over here as well. This is theta over n, and this is theta over n. Now this is 2k pi over n, and this is 2k pi over n. Okay, we can simplify a little bit. You can write it like this. 3 times 3 is 9, so this is it. Okay, now this is a formula that is going to give us how many roots? 3 roots. 1 root for k equal to 0, 1 root for k equal to 1, and 1 root for k equals to 2. So basically you have to take this 0 and substitute it for k here and here, and then simplify. Then take 1 and substitute it here and here, and then simplify, and take k, then 2 and substitute here and here, and then simplify. I mean here at the bottom. Okay, so that's what we're going to get. So there will be 3 roots. When k equals to 0, if you put a 0 there, well, this goes away. So we're just going to get 2 pi 9 and 2 pi 9, and we can simplify it. So when k equals to 1, we're going to end up with, you just have to add, right? So that would be, you see, this was, it was 2 pi over 9, and then you have to add, if k is 1, 2 pi over 3 to it. So 2 pi over 9 plus 2 pi over 3, right? So 2 pi over 9 plus 2 pi over 3. Now 2 pi over 3 with the denominator of 9 would be 6 pi over 9, right? So that's what we do here and here. And that would be 8 pi over 9, and whatever that is, if it's not a nice number, that's okay. You just find what cosine 8 pi over 9 and sine pi over 9 are, 8 pi over 9, and then multiplying, you can write it in rectangular form. And for k equals to 2, again, you do the simplifying and you get another root. So we got 3 roots of that number. All right, now another form for complex numbers that is very useful and is used in many engineering fields is this form right here. Now, exponential form of a complex number. Now, first of all, this right here is called the Euler's formula. Euler, in Calculus 2, you can learn actually the proof of this. How do we know that e to I theta equals to cosine theta plus I sine theta? But for now, just think of it as a function whose input is a complex number, right? So this is r and I, and the output of this is also a complex number, right? So we are working with 4 numbers here. You see, this is a complex number, and the input is a complex number. So you got a function as a complex, takes a complex number to a complex number in the complex plane. So basically, what this is that if theta is pi, right? So what's cosine pi? Cosine pi is -1 and sine pi is 0. So this goes away. So e to I pi is actually -1. So if I write e to I pi, right, that equals to, see, this is 1 and this is 0. So we just get what? I mean -1 and 0, so we get -1. That is also very famous. And if you move the 1 to the other side, you get e to I pi plus 1 equals to 0. 5 important concepts, constants in mathematics are right here. See? e, I, pi, 1, and 0. And this equation relates them all. And it's called the Euler's equation. And this is Euler's formula. Okay, so this formula, basically, notice that this is so e to I, so this is I right here. So for different values of theta, these numbers on the imaginary axis, like I here, so e to I for different theta looks like give us a bunch of complex numbers here in a circle. So for example, if theta is pi, we get that, right? Now what if the theta is 2 pi? So what's cosine 2 pi? 1, and sine 2 pi is 0. So if theta is 2 pi, we get this one, we get 1, right? And if theta is pi over 2, what do we get? Cosine pi over 2 is 0, sine pi over 2 is 1, so we just get I, which is that point right there, and so forth. So this I actually, for different values of theta, it just goes around and becomes a circle right there. Now all of these are going to be explained in other courses when you talk about Fourier transform and application to engineering fields. But for now, we're just going to use it as a form for complex numbers. So since we can write e to I theta as that, and we know that was part of the complex number in polar form, you see, that right there. So if this part of it is e to I theta, that means we can write a complex number as r e to I theta, right? That's another form to write a complex number, and we can do that. All right, so convert to polar form. Well, to convert this to polar form, again, we need r, which is the square root of 1 squared plus square root of 3 squared, right? Square root of negative 1 squared plus square root of 3 squared. That's just 2. So that's 2, and what is theta? Well, theta is tangent inverse of, and this is which quadrant is over here, right? So this complex number is over here. So it's in the second quadrant. That means calculator is going to give you a number, you have to add pi to it. So theta is going to be negative pi over 3 with the calculator, and you add pi to it, so it's 2 pi over 3. So that's it. Now, so in this form, this is what it is, and in exponential form, this is an exponential form. So negative 1 plus I square root of 3 is just 2e to I 2 pi over 3. Okay, so now calculators actually can do this for us. So if you use a calculator and change the calculator in a second, there you go. So if you go and change the mode to, right now is in complex, right? So if I go to, let's say I put negative 1 plus square root of 3i. Now I is right here, and then square root of 3 is right there. Basically I get that, which is in what? Is in this form, right? Is in the rectangular form. Now if I change the mode to exponential form, as you see right there, and do the same thing, press enter, I get what? I get the exponential form of it. And since I'm in degree mode, the angle is given in degree. If I change it in radian mode, then this would be in radian. You see that's 2.0 something, that's the radian for that. And the I is after here, you don't see I, but there is I there, just like there is I here. Okay, so calculator can do this for you, computers can do this for us, but it's very useful. All right, so if I want to, for example, add those two with the calculator, I can add them in that form, or I can add them in that form, right? So if I put it in exponential form, this is what I get, and if I put it in this form, I get this, right? Now, even if it's in exponential form, you don't have to input in exponential form. You can input in this form. Calculator gives the final answer in this form, in exponential form. All right. Now, complex numbers in real life, I'm going to give you one example. For example, in electricity, the state of a circuit element is described by two real numbers, right? But these are much better described by a complex number. What? Well, instead of talking about voltage and the current in a circuit, we can talk about voltage and a current as component of a complex number. So we can think of one complex number that combines the voltage and the current. And also in electronic circuits, we have capacitors, which cause capacitance, and then we have these things, inductors, that cause inductance. Now, instead of talking about this as separate real numbers, we could talk about one complex number that combines the two. And the laws of electricity can be expressed using complex numbers addition and multiplication. So there's a whole lot you can do in electrical engineering with this. And there are other applications here. I'll let you look at it. They're in the notes. I'm just going to move on and talk about parametric equations. Now, before I do that, let's take a look at some of the examples in the text. Let me discard that. So let's see. Now, first of all, we are in. Let's see here. So polar form of complex numbers 8.5. So it's a few examples from exercises in the textbook 8.5. So here are some examples from 8.5. So it says, for the following exercises, find the absolute value of the given complex number. So let's do, for example, number 8, right? So in number 8, basically, absolute value of this number, remember, absolute value means the length of it, and the length is r. So, and that's the square root of a squared plus b squared. That's what that is. Okay? Square root of a squared plus b squared. So here, a is -3, b is -3, so you just put them in there and you get 3 square root of 2. So that is the absolute value of a complex number. For the following, it says write the complex number in polar form. Again, we talked about this. If you can use a calculator, or so here, for example, number 16. There we go. So what's r here? Well, r would be square root of a squared plus b squared, which is just 3, right? Because here there is no a is 0 and b is 3. Now, what's the angle? Now we know this is not in one of the quadrant. 3i is on actually positive y-axis. So obviously the angle is pi over 2. Now if you do the tangent inverse, obviously tangent inverse is undefined, but we know the angle is what is pi over 2. So when the angle is not in one of the quadrants, we can just find the tangent without tangent inverse, because we can easily see what the tangent is. Okay, so here, I mean what the angle is. So the angle is pi over 2, and that's it. And you know cis means cosine pi over 2 plus I sine pi over 2. Alright, and let's go to another set of problems. These are all. So for the following, find the product of two complex numbers. Well, let's do number 24. So to find the product of two complex numbers, we need to multiply the moduli. So the modulus for this is square root of 2, modulus for this is 2 square root of 2. So square root of 2 times square root of 2 is 2, 2 times 2 is 4. So that's the 4 right there. And now the angle is 205 and 118, so we have to add them. 205 plus 118 is 323. So that's all there is to it, right? It's very easy to find. Well, let's do another one. What about 28? So we got 4 and we got 2, and again cis, you can expand it, you know, cis means that. So 4 times 2, and then we add pi over 2 plus pi over 4. We get 3 pi over 4, and we are done. In the following says find the quotient. With the quotient, let's do number 30. So when you divide here, so we got, let's take a look at this. So we got R1 and we got R2. So we divide them, right? And then is cis 90 minus 60, not 60 minus 90, because we are doing Z1 over Z2. So it has to be 90 minus 60. And that's it. So that's the answer. Okay. And let's see. So for the following exercise, find the powers of each complex number. Now, to do the powers, let's do an even one. There you go. So doing this one. So here we see that n is 4. So z is given in polar form, which is pretty good. Otherwise, we have to convert to this before we can use this formula. But it's given in polar form. So that would be just r, which is 2 to the 4th power, which is 16. And then we have to take the angle and multiply it by 4. So 4 times 70 is 280, and that's it. It's that easy. All right. Now let's do one root as well. So evaluate each root. Let's see if we can find an interesting one to evaluate the root. We have an interesting one. No, we don't. So we just do one of these. So let's do number 44. So number 44, it says find the 5th root of z. Okay, 5th root. That means, first of all, first you have to take the 5th root of 32 basically. Or 32 to 1/5 is basically 5th root of, is the 5th root of 32, right? All right, so what is 5th root of 32? Well, it's 2. So we know that. So that would be 2. And then the setup is we have to take the angle, the original angle, and divide it by n, which is in this case 5, and add to it 2k pi divided by the same n. So that's the argument of cosine and sine. They go over here and go over here. And now, If you want the fifth root, you have to find k equal to 0, k equal to 1, k equal to 2, k equal to 3, and k equal to 4. So for every one of these, you have to substitute for k and find one root. So this is going to have 5 roots, right? 5 roots. So those are the 5 roots. So let's look at the 5 roots given right here. So for example, if you put 0 for k here, this goes away, this goes away. So you get cosine pi over 5 and sine pi over 5. We just leave it as what? 2 cis pi over 5. And the second root when k equals to 1 would be pi over 5 plus 2 pi over 5, which is 3 pi over 5. So it would be cis 3 pi over 5. In both of these would be 3 pi over 5. And then when k equals to 2, that would be 4 pi. 4 plus 1 is, it would be 4 pi over 5. When k equals to 2 would be 4 pi over 5 plus 1 is 5 pi over 5, which is pi, right? And then when k equals to 3 would be 6 pi over 5 plus 1 pi over 5 is 7 pi over 5. And when k equals to 4, that would be 8 pi over 5 plus 1 pi over 5 is 9 pi over 5. Alright, so we got all the roots. Alright, so it says find the following exercise, plot the complex number in the complex plane. We know how to do that, right? And then this is just plotting in complex plane, right? That's all there is to it. Alright, there are interesting geometric properties of roots of complex numbers. When you take the root of a complex number, they have an interesting shape, symmetric shape over here when you graph all the roots of complex numbers. So that is the end of this section. So let's move on. So what I'm going to do now, I'm going to continue with parametric equations and talk about what they are, and see if we can put this in one video or two. So let's see. Alright, so what are parametric equations? Well, parametric equations are used when you have an equation in terms of x and y. So if I have something like, if I have x squared plus y squared equals to, I don't know, 5. Well, this is a circle, right? And at radius, let's make it, 4, so radius would be 2. So it's a circle that is centered at 0, 0 and has radius 2, right? So this gives us a picture of what all the points together, what shape they have. But with parametric equations, we know exactly where we are on this shape only if we know one variable is. So that variable, we're going to call it a parameter. So we're going to write x and y in terms of that parameter. Let's say, for example, t. So instead of writing one equation that relates x and y, we're going to write 2 equations, each relate x and t. One relates x and t, and one relates y and t. With 2 equations, but one parameter. So if we can do that, then at every given value of t, we would have a point here, and we know exactly where it is, just by knowing what t is. So that's the use of parametric equations. That's how it changes one equation in terms of 2 variables to 2 equations that are functions of only one parameter. Another advantage of this is that the graph, the points actually, as t changes, the points have an orientation. They either move this way or they move this way depending on the equations that we have. So here, when we graph a circle in terms of x and y, there is no orientation, right? There is no direction. Now here we're going to have direction in terms of a parameter t. So how does this work? So let me show you how this works quickly. So for example, here is so this is a GeoGebra file I created, so we can work with this. So you see the equation in terms of x and y is y equals to x squared. Now, so what I'm going to do, I'm going to let x be t and let y be just t squared, right? And notice that here is t, where I start on t. I start from some number. Let's say I start from let's say -2, and then I'm going to change t, right? So obviously when I'm at -2, there is nothing there because y, there is just 1 point. But as I change t, as you see, there is a orientation, so the points are created in that direction. See, as I change the t, so that these two equations are called the parametric equations for this rectangular equation. Now, of course, they look the same when you graph it for all values of t, but there is a difference. The difference here is that we only have to know one parameter to know where we are on the graph, and also we have an orientation. So, all right, so we come back to this. Let me explain a few more things and then we come back to that. So here we go. It says find parametrization or find parametric equations that model the given situation here. An object travels at a steady rate along a straight line, a straight path, from -5, 3 to 3, -1 in the same plane in 4 seconds. So what we have is a point that moves from a point to another point with a steady rate. So the rate does not change because we were told it's a steady rate. So that means basically it's a straight path, so we can find the slope, or rate is the slope. So what is the slope to go from this point to this point? Well, we know slope is y2 minus y1 over x2 minus x1. So it's -1/2. And we can actually write rectangular equation for the path. A rectangular equation for the path would be y, I'm going to use one of these points as my x1, y1. So it would be y, maybe I use that one, y minus y1 equals to m times x minus x1. So this is the path, rectangular path. Now, to parameterize a rectangular path, the easiest way to parameterize it is to just let x be t, and then let y be a function of that. Make sense? So that's how we parameterize it. That's not the only way. We can go back to that program that this is the same program. We could change that function to -1/2 plus 1/2, and then we can parameterize it this way, or you can parameterize it differently. For example, if you let x be t minus 1, then you also substitute here t minus 1, and you would have a different form, different equations, but the same path. The difference is where you start. Okay, so here's another one. Now this is first what we did. We found the rectangular form of the path, and then we converted it to parameters. parametric equations. We could also start with assuming that each of these is a parametric equation. So x changes according to t and is linear. At, like mx plus b, is at plus b. And then y is also linear because we are told is a steady rate. So x changes with respect to t with some rate, and y changes with respect to t with some rate. Now we don't know what these are, but we know when t equals to 0, we start at this point. So when t equals to 0, x is 5 and y is 3. So when x equals to 0, x is 5 and y is 3. That means when t equals to 0, when t equals to 0, x is negative 5. So we put it there. And then when t equals to 0, y is 3. So we put it there. So now from here we can know what b is and we know what d is. So we know b and d, but we still don't know a and c. But that's okay. Now that we know what b and d are, we put them in here, right? So we know that when t equals to 4, because it says in 4 seconds, right? So when t equals to 4, x is 3 and y is negative 1. So we substitute again in here, x3 when t equals to 4, and y is negative 1 when t equals to 4. So here we go. And from here, we get an equation that shows that a has to be 2 and c has to be negative 1. Because we already know that d equals to 3. So if d equals to 3, then c is going to be negative 1. And we already know b is negative 5 and b is negative 5 here. Then a is going to be 2. Okay, now we found the two equations, right? Now notice this parameterization is different from the previous parameterization. But they give you the same path. Okay? All right. So I'm gonna skip this. It's in the notes. You can watch it. There is a video here you can watch and see how you can parameterize a more complicated path like this. And I have the work here, and also there's a video. I'm going to skip it and move on to the next. Eliminating the parameter in polynomials. So suppose we are given two parametric equations. Now we want to eliminate the parameter and write the parametric equations as a Cartesian equation. So we want to go back to xy equation. How do we do that? Well, to do that, you have to look at the equations and see if you can solve for t in one of them and substitute it in the other one. So for example, here, we can say t is y minus 2, and then substitute y minus 2 here and simplify it, right? So x is t squared plus 1, y is t is y minus 2, so we substitute for t y minus 2, and then go through the simplifying and you get this expression. So this expression is exactly the same path as the path you get when t changes from these two equations. So the Cartesian equation for these parametric equations is given by this. Alright, what about here? Well, here is not as straightforward because how do you solve for t? Well, we can solve for t. All you have to do is use logarithm, right? ln. So it's either you solve for t here and put it in here, or solve for t here and put it there. So in this case, I'm going to solve for t here. So we're going to do x equals to e to negative t, so take ln of both sides, right? So, and that would be ln x equals to, these two cancel each other, so we just get negative t. So t is going to be negative ln x, and you know properties of logarithm, you can put this negative on the top here, make it a power, and then it would be 1 over x. So basically t is ln 1 over x. So we're going to take this and we're going to substitute it in here for t, right here. Now, we know that e and ln again cancel each other, so we left with 3 times 1 over x, which is 3 over x. So the path that these two parametric equations follow is the same path that this Cartesian equation gives us. That's just the same. And as you see again in that program online, the GeoGebra, if you change this, if you change the Cartesian to that 3 over x and change the parametric equations to these two, you see that the path is actually only that part. You're not going to see this part, you're going to see that part depending on what t you have. If you have t values that give you this part, then you're going to see this part too. But you see parametric, path, and then Cartesian. Alright, now with the calculator we can actually graph parametric equations, right? So calculator has a mode here. You can go down here and you see right there, right now is in function mode. You can change it to parametric, polar, or sequence. So let's change it to parametric. Now when you change it to parametric and press y equals 2, you don't see y equals 2 anymore. You see what? You see x of t and y of t, which is x1 and y1t, but that's what it is. So you can put actually square root of t there and put 2t plus 3 there, and now you can graph it. Now we want from t equal to 0 to t equal to 3, right? So we're going to go to window and see t min and t max. We're going to make it 0 to 3, and then we know when t equals to 0, the point that we're going to have is going to be x is going to be 0 and the y is going to be 2 times 0 plus 3, which is 3. And when t equals to 3, we get square root of 3 and 9. So we got 2 points. So basically what we get is we can go to window and change x min. You can change x min to we want to go x from 0 to square root of 3, and y should go from 0 to 9, 3 to 9. So we're going to go a little bit more than that. So let's say 0 to square root of 3 is 1.7, so we just go to 3. And then for y min, let's go to, let's say 1. And then y max, we go to 12. And then graph. So let's see. Let's go to zone 6 first. There we go. So we can trace over it, and as you see, as I change t, x and y change. You see that? So we limited t to be from 0 to 3, but when I went to zoom standard, it changed that. You can change those. So if I want to go to 0 to 5 only, then when you trace over it, you can only go to 0 to 5. But as you see, you get different points for different values of t. Now if you let t be negative, you could also go the other way. So you can trace. Now can t be negative? Can t be negative? No, because Well, you see, domain for t has to be positive values because square root of t is not defined for negative numbers. Now notice there is nothing here. So t cannot be negative, so t has to start from 0. And if you see that the graph doesn't show, you can play with the window and see where you are. Okay? Now, one more thing I was going to show you is the table. If you go to the table set here, you can change the table to be automatically created, or you can ask, so you can put the values in there. So if you put in auto, it's going to start from 0 and go by 1. And these are t values, right? So instead of going by 1, you could go by t by 0.2. And then you press second table. And as you see, for every t value, you get the x and the y values. And that's the table. All right. Application of parametric equations. There are many applications of it, but we talked about that. The point is that when you convert to parametric equations, you have to deal only with one parameter, and also you get the orientation. So now I want to talk about, before I talk about vectors, I want to go back to problems here. So this is parametric equations. So what we have here, let's look at few problems here. It says, for the following, eliminate the parameter t to write the parametric equation as a Cartesian equation. Okay, so here you go. So let's do this one. So what do we do? How do we do this? Well, what we have to do, we have to be able to solve for one variable, for the t in one of them, and substitute it in the other. So here, if you solve for t, for example, from this equation, well, to solve for t is easy. Just write x equals to 6 minus 3t. Move the 3t to this side, and move the x to the other side, and then divide by 3. Now we're going to take this t and substitute it in here for t. So y is going to equal to, so y equals to 10 minus what? T, which is 6 minus x over 3. And then you simplify this. Do the algebra and simplify it. So that's all there is to it. You can multiply by 3 to get rid of that 3, and then, so it would be 3y equals to 30 minus 6 minus x, like that. And then you end up with this right here, if you simplify it. Okay, so that's how we can get rid of a parameter and then go back to a Cartesian form. So there are many of them, like here is another one. In this case, we've got to solve for t in one of them. Well, here we can solve for t here and put it back in here, right? So x equals to 2e to t. So e to t equals to x over 2, right? And then take ln of both sides. So t is going to be ln x over 2. Now we want to take this and substitute it back in here. So y is going to equal to 1 minus 5 ln x over 2. Like that. So that's all there is to it. You see that? All right. So that's how we can do it. All right, now what else? Well, those are all done the same way. So let's do some more problems. Let's see if we can find any more problems here in this section. And here it says rewrite the parametric equation as a Cartesian equation by building an XY table. Now, using XY table. So here, so we can do that, but of course it's easier if you solve for t, right? We did that. Remember, I did 2 examples in the PowerPoint for you. You take 2 values of t and see what x and y you get, and then convert it that way to Cartesian, right? So let me look at one of them. Let's look at this one. So you see, we got these are linear path. So when t equals to 0, right, x is 4 and y is 2. And when x equals to 1, x is 3 and y is 3 times 1 plus 2 is 5. Okay, so we have 2 points, 4, 2 and 3, 5, and we can write an equation for it. Y minus y1 equals to m times x minus x1. And you can pick one of these points to be your x1, y1. Alright, so that doesn't seem to be very difficult. So here, so here's another one. Find for the following exercise parametrize. Parametrize means write it in parametric form. So, and it says using these, x is a cosine theta and y is b sine theta. So here we go. So if we now in the future chapter, we're going to talk about conic sections, ellipses, circles, hyperbolas, parabolas. But for now, this is the shape of an ellipse in rectangular form. So when you convert it, you can easily convert it. How do you convert it? Well, we are told what to do. You see, we are told that we have to use a cosine t and b sine t, right? So if you have a curve like this, and here under the x squared is a squared and this is b squared. That's how we know where a and b are. A and b are under x and y. Then all the same thing. So this is your a squared, this is your b squared. Now we're going to talk more about these when we talk about parametric equations for conic sections. So I'm just going to move on from here and talk about vectors. So let me move on. So what is a vector? Now vectors have many applications. So what is a vector? A vector is a specific quantity drawn as a line segment with an arrowhead at one end. It has an initial point right here where it begins and has a terminal point right here where it ends. So a vector is defined by its magnitude, and which is the length of this line segment, and by its direction. And is indicated, the direction is indicated by the arrowhead. So vectors are used to represent quantities that require 2 numbers. They require 2 numbers. For example, velocity. You can have magnitude of velocity and the direction of it, which direction were you going 50 miles per hour. So now the notation for vectors, we can use lowercase, boldface type, with or without an arrow on the top. All of these are notation for vectors. Given initial point P and the terminal point Q, we can also write it PQ with a little arrow on the top. So now, given an initial point 0, 0 and terminal point A, B, we could also write vectors using this notation, so we don't confuse it with point. So 1, 2 is actually a point, but if I write 1, 2 this way, I mean you start with an initial point of 0 and go to 1, 2. That. So that's 1, 2. So this vector is represented by that. But this point, that point is represented by that. Right? Alright. So it's kind of confusing to work with vectors everywhere in the plane, right? You see, we have vectors everywhere with initial point and terminal point. So there is a way to organize all of these, and that is the standard position of a vector. So the standard position, or the position vector, is given by this. If we have a point, so if we have a vector that goes from initial point C to the terminal point D, then this vector is represented by where it went, the arrowhead, right? So tip minus tail. So we're going to take this and subtract, and take this and subtract that from it. So the vector that we're going to get is going to be the x-coordinate of it, that one is going to be x2 minus x1, and the y component of it would be y2 minus y1. So we get this vector. Now this vector would be the position vector. Always starts from the origin, and that's how we organize the vectors. So if I have a vector that has an initial point here and a terminal point here, what I'm going to do, I'm going to write a vector. Let me do this one more time. So if I have a vector that is, let's say, initial point here, and the terminal point, let's say, is here. So his initial point is 1, 4, and the terminal point is at 4, 5. So what I'm going to do, I'm going to write it this way. So I say this vector is 4 minus 1 is 3, and 5 minus 4 is 1. Now 3, 1 is this right here. This vector right here. Now notice that this vector is basically the same length as that one, right? Is the same length of that one as that one, and is in the same direction. The only difference is here, the only difference is that this is in the standard position. So if I have another vector here, I can also put that, with the initial point here, I can also put that one over here. If I have another vector here, I can put it here. If I have a vector over there, I can put it here. So all the vectors can be organized with the initial point of the origin. That's what this does for us. So here's an example of, you see, let me get rid of my pen so I can click on this. And here we can change these vectors, right? So I can change this initial point anywhere here, and then terminal point anywhere, and you see that vector right there is the standard position of the same vector. So we can take any vector anywhere, right? If it's over there and over here, doesn't matter. Any vector has a standard position representation using this formula, right? x2 minus x1 comma y2 minus y1. But remember, we use these little symbols instead of parentheses to represent a vector. Okay, so now what is the magnitude of a vector? Magnitude of a vector is represented by absolute value of it, and that is just square root of a squared plus b squared. If a and b are components of the vector, then that would be a square root of a squared plus b squared. So the direction for the vector is basically tangent inverse of b over a. Right? Again, the same thing applies if you're in the first and fourth quadrant, then this calculator gives you the correct theta. But if the vector is here or here, calculator, you have to add pi to it to get the correct direction, right? Other than that, that's it. That is that's the magnitude of a vector. That's how it is calculated. So it says find the magnitude and direction of the vector. Well, it's very easy. The magnitude is the square root of, first we have to write it in a standard form. So this is Q, PQ. So PQ, by the way, PQ is different from QP, right? So the direction is different. So we want PQ. P is the initial and Q is the end point, the terminal point. So it would be Q minus P. So it would be -2 minus -8. What's -2 minus -8? That's 6. And then -5 minus -1, which is -1, which is -6. So this is in component form, x and y component. Okay, so what's the magnitude of this? Would be absolute value of it, which is the square root of 72, right? 6 squared plus 6 squared is 72. Now what's the direction of this? The direction, where is this vector? This vector is over here in the fourth quadrant, so the calculator gives us the correct answer. So tangent inverse of y over x or b over a is -45. So the direction is, now the direction should be the smallest positive angle that the vector makes with the positive x-axis. Because this way, so we know exactly what we are talking about. So we want to standardize that one too. So when we give the angle, we give an angle that is the smallest positive angle that a vector makes with the positive x-axis. Now this is not, of course, because that would be a negative angle. That's not a positive angle. So positive, I mean from here. So that angle is going to be, well, we know if this is -45, then it's going to be 315 degrees. So the direction for the position vector is going to be 315 degrees. So everybody knows that means you make an angle from the positive x-axis in the positive direction to get to it. Now -45 is not wrong, but it's not conventional. Alright, how do we add and subtract vectors? Well, we can do it geometrically. So we can do it. So what we can do, if we have two vectors u and v, we can take v and then put u and put v right here, right after u ends. We put the initial point of v and then draw it in the direction that v has. And then from the initial point of u to the terminal point of v, that is the resultant vector. That's the sum of the vector u and v. That's one way to do it. It is tip to tail geometrically. Another way to do it geometrically is like this. So here is u, a and b. Let's say this is two vectors we want to add. So A and B. This is A and B. And so the way we do it is we put both of them here with the initial point at the origin, or share the initial point, and then we make a parallelogram with the vectors as two sides, and the diagonal of the parallelogram is the resultant vector, or the sum. So if you click on these, you can see them online, and you can actually change these. So tip to tail, you change these vectors and you see that's tip to tail method. Now parallelogram method would be, if I change that, you see no matter where the two vectors are, the resultant vector is always that diagonal right there. And this is the tip to tail. You can change these and you get the sum of, so this green one is the sum of these two vectors. Now geometry is helpful to understand what's going on, but what we like to use algebra. So given two vectors in these forms, and notice these are not parentheses, so these are vectors, find two new vectors, u plus v and u minus v. So the way we add and subtract vectors using algebra is by just adding the components and subtracting the components. So u plus v would be basically 3 plus -1, comma -2 plus 4. So it sees 2, 2. And if you do it with geometrically, if you draw them in the coordinate plane and do it geometrically, you get the same answer. Now what about u minus v? We just subtract them, so it would be we just subtract them. So instead of subtracting, you can add the opposite. So u minus v is the same as u plus -v, and -v is just the opposite of that vector. You multiply the components by negative. So that was -1, 4. So when you put a negative here, you multiply it by negative and by negative. So we get that. And then when you add them, you get 4, -6, and that's, you see, that's the u minus v. All right. So each component of the vector is multiplied by the scalar. When you want to multiply a number by a vector, just multiply the components by that number. That's all. So only magnitude changes, but not the direction. So here's an example. So here's a vector. You want to find 3 times v, 1/2 times v, -1 times v. That's okay. Just multiply those numbers by that vector. So 3v would be 3 times 3 and 3 times 1. That's it. So that's 3v. You see it's 3 times bigger. And then 1/2 v would be 1/2 times 3, 1/2 times 1. And you see is almost half long, half as long as that one. And then -v, the value doesn't change, but it changes direction. You see it was that way, now it's this way. So when you multiply a vector by a negative, it changes direction. Okay? So find the components of the vector v with initial point 3,2 and the terminal point 7,4. Alright, well we know how to do it. Now remember, is the terminal minus the initial. So it's going to be 7 minus 3 and then 4 minus 2. So that's it. Unit vectors. What are unit vectors? Well, unit vectors are vectors that have the magnitude of 1. Now there are two famous unit vectors. One of them is in the direction of x-axis, positive x-axis, which is here, and the other one is in the direction of positive y-axis. These have names. This one is called I, not the I from complex numbers, right? This is I here. And then j is this vector right here that is in the direction of positive y-axis. So this is in the direction of positive x-axis, and its length is 1 unit. So I know it looks like 3 squares, but we assume this is number 1. Okay, so in this direction, the coordinates of that point would be, of course, 1, 0. So when I write that, I mean this point, 1, 0. But when we write it with this triangle thing, 1, 0, that means the vector what? The vector I. So I is a vector 1, 0, which is a unit vector in the direction of positive x-axis. And j is a unit vector in the direction of positive y-axis. Now the good thing is that we can use these two to write, we can use these two vectors to break every vector in the coordinate plane into two components that have basically certain multiples of I and certain multiples of j. So any vector can be broken down into bunch of i's plus bunch of j's. For example, see this vector 2, 3 can be written as 2, 1, 0 plus 3, 0, 1. Right? Now when you multiply, you get the same thing, because 2 times 1, 0 is just 2, 0. Right? And then 3 times that is just 0, 3. And then when you add these two vectors, right, we're going to get what? 2 plus 0 is 2, and 3 plus 0 is 3. You get the same vector. But this way, we can write this vector as 2i plus 3j, right? It's easier if you write them that way. Again, don't confuse it with what? With complex numbers. These are vectors, right? Now, to do that, to make sure we understand that, we put a hat on the top of I, put a hat on the top of j, so we understand that these are vectors. Or we just make them bold-faced. Alright, so now if we have a vector that is not unit vector, let's say we have a vector that is not unit vector, we can actually make it a unit vector by dividing by its magnitude. So if we have a vector, let's say this vector, its magnitude is not 1. How do we know? Because we know absolute value of v is actually square root of negative 5 squared plus 12 squared, which is 144. So that's actually square root of 169, which is 13. So magnitude is not obviously 1. So, but can we make the magnitude 1? And the answer is yes, easily. All we have to do is what? Divide by its own magnitude. So here is the vector v. If we take vector v and divide it by its own magnitude, then the magnitude of it would be 1. Right? So this would be a vector whose magnitude is 1, but whose direction is the same as this vector. So if this vector is this way, the vector that we're going to find here is going to be a unit vector in the direction of what? Of this vector. So if this is v, this little vector here would be v divided by absolute value of v. So that's called the, you see that little one right there? That's what this vector is. So it could be written in this form, or if you don't want to put the plus sign between them, you have to put a comma and use this notation, right? So either we use ij notation or that notation. Now in calculus 3, since we have 3 axes, we have x, y, z in 3D. This is x, this is y, this is z. Then we have three of these. We have I, we have j, oops. What did I do? I don't know. So let me go back. There you go. I'm gonna have to go back to, I don't know what I did. Almost done with this. There you go. See here? Yes. Okay, so so we have two different notation. I lost my pen. Let me find it. Here we go. So we have two different notation. That one and this one right here, right? And both of those are vectors. Now, as I was saying, in calculus 3, we have x, y, and z. So we have I, which is basically here. And then we have j. And then we have k in the direction of z. And then we can write all the vectors in 3D in terms of I, j, k. But that's calculus 3. But it's not pre-calculus. All right, given a vector with initial and terminal point, we can actually write it in this form, right? Write it in this form. So every basically vector can be broken down into those. So think of, you want to go diagonally, but you can. You have to either go horizontally or vertically. So this way we can get anywhere by going horizontally and then vertically. I could go there by going horizontally and then vertically. Or we could go vertically and then horizontally. So that means basically these are directions how to get to a point in the plane. So when I write 2i plus 3j, it means start from here and go 2i to the right and go 3j up. All right. Write the vector in terms of I and j. So if you have two vectors, the initial and terminal points, you want to write them in terms of I and j. Well, first we have to write them in the form, in this form, right? So this vector would be what? This vector would be negative 6 minus 2, which is negative 8, and then 6 minus negative 6, which is 12. And now this vector can be written in terms of ij. So that would be negative 8i plus 12j. That's it. So first we can write it in this form and then convert it to ij form. So adding vectors and subtracting vectors in ij form is very easy. You just subtract the i's and j's and you have the answer, right? So for example, 2i minus 3j plus 4i plus 5j, just add the i's and add the j's and you have the answer. Now remember, these could be two velocities, and then you add them, you get resultant velocity. These could be two forces applied to a point. These could be forces in physics, like F1 and F2. When you add them, you get the resultant force. So there are many, many applications in many, many fields. Vector components in terms of magnitude and direction. Now, we said that vectors have magnitude and direction. So the magnitude of a vector is given, of course, by absolute value of v. What is the direction? How do you find the direction of a vector? Well, the direction of a vector, remember, we know about a point right here in terms of sine and cosine. Remember from previous chapters, if this is r, the coordinate of this would be r cosine r sine. But instead of r, we can make that absolute value of v. If I make that absolute value of v, then the horizontal component would be nothing but what? It would be nothing but that cosine theta. And the vertical component right there, that number would be, that length would be that sine theta. And theta is the angle that this thing makes with the positive x-axis. So now we can write this what? This is xi plus yi, if they write it that way. You can use a and b if you want, doesn't matter. So here our x is that, and our y is that. So now we can write it in terms of the direction of the vector. So we got the direction of the vector, which is that theta, right? All right, now from here, of course, if you know x, then you know cosine theta is x over absolute value of v, and sine theta is y over absolute value of v. So write a vector with length 7 at an angle of 135 to the positive x-axis in terms of magnitude and direction. Well, that's easy. So that means we have a vector that 135 is about right there, and the magnitude of it is 7. So it's a vector that is right there. So that's the vector. Well, all we have to do is write the components, and the components are going to be, well, we have to find out what this angle is, but we are given what the angle is, 135. So this would be 7 cosine 135, and this component would be 7 sine 135, right? That's it. So we got cosine, 7 cosine 135 is x, and 7 sine 135 is the y. So it's given this much in the x direction, this much in the y direction. Of course, this one would be a negative number, and this one is positive number. All right, for example, if you throw something with certain angle, then the path of the object can be explained using the horizontal and vertical component of the velocity. If this is the initial velocity, v sub 0, then this one would be absolute value of v sub 0 cosine theta, and that the vertical component would be absolute value of v sub 0 sine theta. So those are what? Those are in terms of the velocity. So that's the horizontal velocity component of the velocity, that's the vertical component. So as this thing goes up and comes back down, there is a velocity that's pushing it this way, that's horizontal velocity, and there is a velocity that's pushing it up, that's the vertical component of the velocity. Of course, eventually gravity is going to get rid of that component and make it come back down. But this horizontal one keeps going until it hits the ground, right? So you see many, many uses of these concepts in physics. All right, so dot product is the last thing I want to talk about, and that is basically when you take two vectors and you multiply two vectors. How do we multiply two vectors? Well, there are two ways to multiply two vectors. One way we're going to talk about here, and that is called the dot product. So the dot product of two vectors is given by this definition. If you have two vectors in component forms, just multiply the components and add them. So the dot product, the result, is not a vector, but is a number. Now, what it means in different fields has many applications, but for now we just want to understand how to do this operation, dot product. Basically, if you have two vectors v and w, the dot product is a number that tells you how much these vectors are in the same direction. Basically, you can think of it that way. So the dot product of two vectors is kind of a number that measures how much the two vectors are in the same direction. For example, if they are in completely opposite directions, the dot product would be, so what would the dot product be if they're completely in opposite direction? Well, it turns out that to find the angle between two vectors, we use this idea that cosine of the angle is equal to this. So where this formula comes from is a different story that we're not talking about here, but I'm not telling you that story. I'm just saying that there's an operation we can do with vectors that is very useful. So here there are two ways to do it. One way is using the components. Another way is to use the magnitude of the vectors and the angle between them. So v dot w, you can think of it as this operation. So cosine theta times the absolute value of v times absolute value of w, using Pythagorean property. So so there are two ways to find the dot product of a vector. So two vectors. So let's do it. So here are two vectors. They're given in terms of I and j, but you can easily convert those to what? Component form. Like 5, 2, and this one is just 3, 7 if you use commas, right? So the dot product of these two would be 5 times 3 plus 2 times 7, which is 29. That's it. That's the dot product. Now, so what is the angle between them? Now, as we said, there's another way to do dot product. So if you call this v1 dot v2, we know that this would be absolute value of v times absolute value of v1 and v2, and the cosine of the angle between them. So the cosine of the angle between them is equal to v1 dot v2 divided by what? Absolute value of v1 times absolute value of v2. And then to find the theta, we just do the cosine inverse of this. So what is the absolute value of v1? Is the square root of 25 plus 4, which is square root of 29. What's the absolute value of v2? Square root of 9 plus 49, which is 58. Square root of 58. So those are those two in the denominator. Now we have to also dot product, right? We have to do the dot product of that dot that, which is 5 times 3 plus 2 times 7, so which is 29. We already know that. So that would be 29 divided by what? Divided by square root 29 times square root 58, which is that. And if we take cosine inverse of that, we're going to get this angle. So that's the direction. I mean, cosine inverse of this number would be 45, which is the direction of this vector, right? Now here, what we are doing here is basically we are using dot product between these two. So you can do that too, but you don't have to. You can use this formula here, right? So v1 dot v2, the numerator was 29, right? That's the numerator, and the denominator is that. So basically, we are finding cosine inverse of this with the calculator. All right, so and that's the angle between the two vectors. So angle between the cosine of the angle between two vectors is given again by v dot w, and then absolute value of v times absolute value of w. All right, so find the angle between those two. Again, same thing. Use that formula, cosine inverse of that expression. You first find u dot v, which is negative 3 times 5 plus 4 times 12, right? 48 plus negative 15 is 33, right? And then the absolute value of this one would be square root of 9 plus 16, 25. And this one would be square root of 25 plus 144. So that's 5 and that's 13, right? So they go in the denominator, and that's it. So you don't have to separate it like this. You could just work on it right here. Just multiply these two and then dot product those two. So it would be 5 times 13, which is 65, and the dot product is 33, and that's it, you're done. And take the cosine inverse. And the angle between them is 59.5. All right, and here's an example of that is in the text, where we are given a projectile that is thrown with a certain velocity v sub 0. So the horizontal movement of this projectile is given by, when we say projectile, it means they throw it, it doesn't have an engine on it, right? It's just with the initial velocity, and then nothing else acts on it except for gravity. And if you throw a projectile with that angle, then the horizontal movement of it is given by that, which basically means how far this object is going to go in this. You see, the object is here, right? How far is going to go horizontally basically is the velocity horizontally, which is v sub 0 cosine theta. And then if you multiply the velocity by t, you get what? You get the distance that it travels. Now, how far does it go up? Well, it's going to be what the gravity does to it, which is negative. The gravity is going to pull it down that much, plus this is the vertical component of the initial velocity we give it. So v sub 0 times sine theta. That's that part. If you add that, plus what the gravity is doing to it, which is pulling it down, this is pulling it up, plus what it was to begin with. Now, if it's at 0, then h is 0. But if you start from here, then h is going to be that number. Okay? So we are given a bunch of numbers. You just substitute those numbers in these equations, and you can find the paths, parametric equations for the path of the object. Okay? And again, this is in the notes, and you can I'm sure in the next slide I'm gonna show you the path of it. But here you see the initial velocity is 95 feet, so that goes for that v sub 0, and then 52 degrees goes for theta, and that's it. So you can write the equations for that right here. So these are the equations for the path of this object. And now let's look at it. Let me get rid of my pen so I can click on this. Discard it. Looks like you've opened it already. it in. So let's go back to it. There you go. So you see, these are the equations, and so this is the object. So at different times, see where the object is going to be at that time. See, with that velocity. So it's not gonna, if it's, so this is the, oh, this is the speed. I'm changing the speed actually. I didn't want to do that. So let me make it back to, put it back to 90, was it 95? Yeah. Make it back to 95, that's the speed. I meant to move this. So you see, at different times, you see where the object is. See that? So what allows us to do this is this ideas we talked about in this section on vectors. You see, we know exactly where that thing is because we know the parametric equations for the path. When time changes, we know exactly where that thing is, and we know which direction is moving, right? That's how we can get 3 numbers, 4 numbers from Mars and know which direction the vehicle is moving on the Mars. And that's just like magic, but it's not, of course, as math. All right, so very few more minutes only, and this is the section on parametric equations. So we got, I want to do few on the vectors. And so here it says, given a vector with initial point and the terminal point, find an equivalent vector whose initial point is 0, 0. Write the vector in component form. By that they mean what? Initial point 0, 0 means a standard position. So you just have to subtract, right? So it would be 3 minus negative 4 and negative 3 minus 2, right? So this section, really, I did examples from this section for you. So I think we can actually stop this video here, and we are, I guess, finished. We finished chapter 8, and next video I continue. Okay, so take care of yourself, and I see you in the next video.